This video, we're going to be looking at graphing tangent functions. And again, in class, we've done like a little tangent exploration activity. Tan's sort of the odd function out there in terms of its vibe. And so in terms of recognizing why tangent function looks like this, it helps to remind ourselves that tangent as a function is just the ratio between sine of x and cos of x. So tangent actually is a rational function, right? Where you have two functions being divided into each other. And of course, as soon as you have that, any time your denominator evaluates to 0, because remember, in this case, your basic tangent function has cosine as its denominator, you cannot have your denominator equaling to 0. And so as soon as you recognize that, that starts manifesting itself, and that's why you get this connection with, okay, my tangent function is going to have vertical asymptotes because I'm going to have all these x values that evaluate to 0 that the function can never have as an input. So that's basically what's happening here. So when you're doing these functions, one of the first things to recognize is, okay, where are my vertical asymptotes happening? And they happen whenever your denominator is equal to 0. And so you can find them quickly by finding that. And then in terms of sketching these out, these middle tan lines here, these tangent curves that occur between every single vertical asymptote, basically they are going to start near the vertical asymptote and end near the other vertical asymptote. There's 3 anchor points that we like to use with tangent. Basically, they are 0, 0, and then the pi over 4s. And of course, they're coming from your 45, 45 degree or pi over 4 triangle where you have 1, 1, root 2, because tan of 45 and tan of 45 both evaluate to 1 over 1, which makes these kind of nice anchor points to reference back to. The distance between your anchor points is going to be your amplitude. So again, this vertical distance here is whatever our amplitude, and I'm kind of using amplitude a little bit loosely here, but it's that vertical stretch, that number that occurs in front of the tangent function. Yeah, so let's kind of just dive right in. And again, so I've got some, you can see here, I erased what we did in class there. So let's kind of take this one nice and slow here. So again, I'll start by kind of graphing out the vertical asymptote. So tan of x minus pi thirds is the same thing as sine x minus pi thirds over cos x minus pi thirds plus 2. Okay, that's really what that is saying. So as soon as you get that, you're like, oh, okay, I know that this cannot evaluate to 0. So we can say cos of x minus pi thirds cannot be equal to 0. So then we ask ourselves, okay, when does cosine evaluate to 0, or, cos of negative, cos to, the inverse of cos of 0 is equal to x minus pi thirds. Well, what's the inverse of cos of 0? That must be, so when does cosine equal to 0 is maybe a better way of saying that. And so cos is equal to 0. Well, let's pick one here at pi over 2. Of course, there's lots of different answers, but I'm going to start with the first one, which is pi over 2. So pi over 2 is equal to x minus pi thirds. So I'm going to move this one over, this x minus pi thirds. So I'm going to add x pi thirds to both sides. I'm going to add x pi thirds. So pi, what is that? X pi thirds. So you got what? 3 over 2 plus, or 3 over 6 plus 2 over 6 gives you 5 over 6. So x 5 pi over 6. Or is basically, and these should all be like cannot equal. X cannot equal to 5 pi over 6. So if I go here, is that not gonna, I need this to enhance. Can't really see that, can you? So I can't read these. This must be a lower resolution image for whatever reason. I think 5 pi over 6 was right here, though, if I had to take a guess. I'm going to call that 5 pi over 6. We'll say that's 5 pi over 6. And then because I don't have a a horizontal stretch, every pi is going to be where cos is going to be equal to 0. So you think back to your unit circle there. So at 90 degrees, you're pi over 2, and at 3 pi over 2, you're going to have cosine evaluating to 0. So I'm going to minus pi, and I'll get this point right here. Excuse me. And I'm going to add pi, and I think I'm going to get this point right here. Again, so let's just, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, need to move 1 over. Take me to right to here. 6. Okay. And then, so normally I'm have like 0, 0 as an anchor point, but I'm going to move pi thirds over and up 2. So moving pi thirds over and up 2. So pi thirds looks like it's roughly, well, actually I can just go right to the middle of between these two and that's going to tell me. So literally exactly in the middle is going to be my middle point. And I want to go up 2, which takes me right to here. And then I'm going to go over 1, down 1, go over 1, down 1, because my amplitude is just 1. So something that looks like this looks like the way it should look. And again, that pattern repeats itself, so I can just kind of copy that pattern, something that looks like this right here. Well, let's do another one. So here I have tan of 1/2 x plus 2. So if I look at this right here, again, I'm going to say to myself, okay, cos of 1/2 x cannot be equal to 0. So cos of -1 of 0, the inverse of cos of 0 cannot equal to 1/2 x. Take the inverse. So this will be pi over 2, cannot equal to 1/2 x, or times it by 2 gives me pi cannot equal to x. And by the way, I'm realizing that like it does happen every pi over 2 because something else is happening here that I have to remember to incorporate. So this is plus pi n. Now when I add pi thirds, it doesn't change that pi n. Here though, I have to remember that it's happening every pi n. When I times by 2, it affects not only this term, it also affects this pi n, so it's actually every 2 pi n now. So in terms of when these are happening, they're happening at pi and then plus 2 pi n, just because of the nature of these functions, right? Like if it's been very stretched out because only half a wavelength is occurring where one wavelength used to occur before. So I'm going to find pi, which looks like it's right here, and then minus pi minus 2 pi takes me right to here. So perfectly in the middle, which makes sense, right? Because there's no horizontal translation here. So I still have 0, 0, but I'm going to move it up 2 because I have that vertical translation of 2. And then basically a quarter, so like halfway between these points is going to be the second point. And then, oh, that should be, it's not, this would be like this if it was reflected. It would be right here. And then halfway between these points would be the other point. And so I've got something that looks like this. And again, that rinses and repeats, you know, on this side and on that side. And again, just to be clear, like I know this distance is going to be 1 because that's my number in front of the tan, whatever that vertical stretch is, that'll be manifesting itself between these anchor points. And like I can cut this tangent graph kind of into quarters there once I recognize where my vertical asymptote is, where perfectly in the middle is that primary anchor point of 0, 0, however it's been translated 2 up in this case. And then in between the vertical asymptote and that middle anchor point is another anchor point where that pi over 4 comma 1 normally is. But again, it's been shifted up 2. And it's been stretched out because of that number right there. These graphs don't really change much more than this. Like I don't want this video to run a million years long, so I'm gonna tie it off right there. And please check out your OneNotes if you're looking for practice. I'll see you guys in the next video.